the function, and then corresponding changes take place in the graph. And 2.7 is just about seeing connections between changes in one place and changes in the other. So if we have y equals x squared, like this, y equals x squared, and we want to transform that by adding 2 to the right hand side, what's that going to do to the graph? What the graph we see right here is the graph of y equals x squared. What's the graph of y equals x squared plus 2 going to look like? Is it the left? Now there's a plus 2 that does take us to the left, but it's when there's an x plus 2 on the inside. Let's look and see. If we go and add 2, it's going to go 2 units up. So y equals x squared plus 2, the y coordinates are 2 units greater than they are in the original, so it takes the graph 2 units up. On the other hand, we do the opposite. If we subtract 2, it'll take the graph 2 units down. So it's vertical. It doesn't distort the size or the shape of the graph. It's a rigid transformation, just slides it up, slides it down by adding a number to go up or subtracting a number to go down. Now, if we want to shift the graph to the right or to the left, we want to think of it as a substitution. Now you could, if you wanted to, think of it as adding a number on the inside or subtracting a number on the inside, but it's better, way better in fact, to think of it as substituting x minus a number for x or x plus a number for x. So if we substitute x minus 1, x minus 2, x minus 3, the graph shifts in kind of the opposite direction that my intuition would tell me it should go. I see that minus, and I'm thinking, well, it's affecting the x coordinate, so I would think it's affecting the x coordinate in the negative x direction, which would seem to be to the left. But which way is this graph going? I go x minus 4, x minus 5 is going to the right. And the reason we'll see, if we haven't already seen, is that x has to be, on the blue graph, 5 units greater than it would have to be on the black graph to make up for the fact we're going to subtract 5 before we square. So if we're wondering what value of x, what value of x would give us 0 as the answer, well, on the original graph, x equals 0 would do that, but here x has to be 5 because we're going to subtract 5 before we square. So the x values on the blue graph have to be 5 units greater than the x values on the black graph because of the minus 5. So it's to compensate for the minus 5. Really, that's why we go 5 units to the right, and I think that's maybe a good way to think about this. So we looked at those, basically, we populated a list of 4 transformations last time, and I didn't see where I had written them down, so I'm going to begin today with just repopulating that list. So someone need a number from 2 to 9.
7.
What did you say?
7.
7. So 7. So y equals f of x. Several different things, 8 different things actually we're going to do with that 7, and then a couple things we're going to do without the 7. What if we add 7 to the right hand side? I want to see what does that do to the graph. Well, what we're going to do, or what that's going to do, is it's going to shift the graph 7 units up, down, right, or left? Up. It's going to add 7 to every y coordinate. See, y started out being just f of x, but in the new one, y is f of x plus 7, 7 greater than that, so y is 7 units greater, so 7 units up. If we do the opposite of that, subtract 7 instead of adding 7, we're going to shift the graph 7 units down. Okay, because the y coordinates will all be 7 units less than they were originally. If we want to shift the graph to the right or to the left, the action has to be on the inside of the parentheses there. And I'm going to keep saying this, and if the experience of my 8 o'clock class is any indication, I'm probably not going to say it enough, but I'm going to keep saying it. Think of it as a substitution, not a subtraction. Substitute x minus 7 for x, wherever we see an x, in the rule defining the function, and it will shift the graph 7 units. Which way in this case? My hearing, I just get old. To the right, yes, exactly. To the right. And do the opposite of that. Y equals f of the quantity x plus 7. That will shift the graph 7 units to the left. 7 units to the left. So these are the first 4, and these are all rigid transformations. They don't distort the size or the shape, just shift the graph up, down, right, or left. We did some of those last time, so hopefully that was helpful. Helpful review. Did I call attention to the misprint that existed in that B example last time? I believe we did that. All right. On in to the vertical stretches and shrinkings, also called compressions. I want to illustrate this with a different GeoGebra worksheet. We're going to do something else with that 7 in a moment. I'm going to close this one out. Actually open a new one and it'll automatically close this one. Don't save it. Instead, give me the semicircle. All right. So what we have is the semicircle whose equation is y equals the square root of negative x squared plus 9. What I'm going to do is multiply the right-hand side by 2 and have 2 times the square root of negative x squared plus 9. When I do that, what's going to happen to points on the graph? Y starts out being what it is, square root of negative x squared plus 9. After the transformation, all the y coordinates are going to be twice that, twice what they originally were. So, whereas we start with, seems like we did this last time. Did we do this last time? I just didn't see. My 8 o'clock class is behind where you all, but I wasn't sure just how far behind. Let's go ahead and go through this. Y equals 7 times f of x. We're going to stretch the graph vertically by a factor of 7. And y equals f of x. Y equals 1/7 f of x. We're going to shrink the graph vertically by a factor of 1/7. So since I have it open, stretch vertically, does like that. Shrink it vertically, it does something more like that. Shrink it vertically, multiply by a number that's between 0 and 1. That's not 1/7. 1/7 would be way down here somewhere. Really shrinks it vertically. And that's not even 1/7. I guess that's 2/10, a little bit more than 1/7. Did we do the horizontal stretches and shrinkings? Y equals f of x. Y equals f of 7x. Y equals f of x. Y equals f of 1/7 x. Did we do those? Substituting 7x for x or 1/7 x for x? Just looked at what we did last time. I didn't see that. Let's see. I'm going to go back to the original one here. I can make it stop at 1. There we go. And if we have y equals the square root of negative x squared plus 9, I want to see if I can predict what would happen if I substitute 2x for x wherever I see an x. Pick up the x, replace it with 2x. 7x would be kind of extreme. Good for the list of all 10 transformations, but 2x, I think we can actually see this on this picture. In the original, if I substitute 3 for x, square the 3, get 9. Multiply 9 by -1, get -9. Add 9 and get 0. And then take the square root of 0. What do I get? What's the square root of 0? 0. So that results in this point on the graph, the point 3, 0. On this new graph, which we'll see in just a moment, we didn't already see last time, what x value would give me that same y coordinate? I don't feel bad. The 8 o'clock class couldn't figure it out either, so it must not be trivial. What x value could we multiply by 2, square, multiply by -1, add 9, take the square root, and still get 0? Well, simplify that a little bit. We're substituting 3 for x right there. So basically, 2x would have to have a value of 3. That's a hint. If 2x has to have a value of 3, what would x have to be? 3 over 2, or maybe 1.5? So, if I substitute 2x for x, it means x can get by with being only half as great as it had to be before, because you're going to multiply by 2 before we square, multiply by -1, and add 9, take the square root, and all that other stuff that we do. So the x values actually get smaller, closer to 0, half as far from 0 as they originally were. Let's see what effect that has on the graph. Basically, that point is going to get pushed right there. And a point maybe right here is going to get pushed right there. And a point right here is going to get pushed right there. Points on the y-axis are going to stay put, and the graph is going to look like this. The other half of the graph, there, let's see, there, it's going to look like that. We're compressing the graph horizontally by a factor of 1/2 just by substituting 2x for x. It's counterintuitive. It's the opposite of what I would think. Maybe it's the opposite of what you would think. Just like substituting x plus 2 for x sends the graph to the left, substituting 2x for x cuts all the x coordinates in half. All right, let's see this transformation in action. See, I'm going to replace that 1x with a 2x. Here goes. What you get shrunk horizontally by a factor of 1/2. Keep doing that, it keeps shrinking it. Substitute 3x for x, it'll shrink it horizontally by a factor of 1/3. Substitute 5x for x, it shrinks it horizontally by a factor of 1/5. Basically multiplying all the x coordinates by 0.2, 1/5. So this will, in spite of the 7x there, it looks like we're multiplying all the x coordinates by 7. Really, the x coordinates get to be 1/7 as great as they were originally. So this will be a shrinking. We will shrink the graph horizontally by a factor of 1/7. Multiply all the x coordinates by 1/7. And what if we substituted 1/7 x for x? Any thoughts as to what would happen there? It would be the opposite of a shrinking. Imagine this. X equals 3. And we substitute 3 for x. We get f of 3, and they give us the y value. If we want that same y value, what would x have to be right there to make that happen? To give that same y value, whatever f of 3 is. What x value would do it for us? Well, it would have to be that when we multiplied by 1/7, we get 3. So 3 is 1/7 of what number? 21. 21. X would have to be 21. So if we look at the original graph, it looks like this. Then after the horizontal stretch, x is 7 times as far from 0. And a negative x would be 7 times as far from 0. So we stretch horizontally by a factor of 7. Well, in this picture we can't go quite that much, but I can take the 5x and replace it with 0.5x, 1/2 x, and that'll stretch horizontally by a factor of 2. So let's go from there to 0.5. Oops, 0.5, 0.4. Come on, stop there. What I should do, I guess, is just stretch this out so it's a lot wider and easier to manage. There we go. There. So, replace the x with 0.5x, and x has to be twice as great as it would originally in order to get the same y value. An x value of 3 makes this one 0, but it takes x equals 6 to make this one 0, because it's going to take half of 6 before we square. Multiply by -1, add 9, take the square root. So it's counterintuitive, but when it happens on the inside next to the x, that's the way it happens. It is. Did we do these last time? Example 6. Did we do this picture? Graph this on the calculator? All right, let's look at this one then. So here's the vertical stretch, and then we'll look at also the horizontal stretch and shrinking. So good. Turn off that view. And y equals, go ahead and clear that one. And for the original function here, f of x equals x plus 2 times x minus 3 times x minus 5. You can type that directly into your y1 equals directly into the y1 equals. If you press graph, the standard viewing window, if your calculator is in the standard viewing window, won't show you a whole lot of it. It just this little portion of it. So it'll have a tendency to zip up and down through the standard viewing window. It's better if you go in to the window and change it to this. Change it so the x-min and x-max can stay the same. They're fine. But the y-min and y-max, it's better if you make them y-min equals -40 and y-max equals +60. And the y-scale, I like to change the y-scale along with the y-min and y-max if we make them bigger, so the y-axis isn't cluttered with tick marks. So +10 for the y-scale would be good. So if you change the window settings to that, you ought to see the graph of this one. This is the graph of the original function. And what we want to do is compare that to the graph of y equals 2 times that original function and see if we can see the vertical stretch take place. So y equals 2 times f of x would be y equals 2 times x plus 2 times x minus 3 times x minus 5. So I'll type that into y2. y2 is going to be 2 times x plus 2 times x minus 3 times x minus 5. Well, let's see, wait. I didn't craft the original yet. Okay, so here are both of them. Here is the original. No, it's not. That's the stretched version. What? Oh, the original is turned off. So now it looks like a shrinking. Let's get this in the proper order. Here's the original. Let's make note of the intercepts. The y-intercept of the original graph here is 30, and the x-intercepts are -2, +3, and +5. If we look at the vertically stretched version, it'll look like this. Turn it back on. Graph. Two things to observe. the x-intercepts stay put. If you're stretching a graph vertically, it moves points twice as far from the x-axis as they originally were. But if the points are already on the x-axis, their y-coordinates are 0. If you double their 0 y-coordinates, they're still 0. So -2, 0 is still an x-intercept. 3, 0 is still an x-intercept, and 5, 0 is still an x-intercept. The y-intercept, though, moves twice as far. You've got 0, 30. The y-intercept of the stretched graph, vertically stretched, is 60. And another key point on the graph, if you evaluate the function at 4, you'll notice that the point 4, -6 is on the graph of the original function. If we stretch it, the point 4, -12 is seen to be on the graph of the vertical stretch. So it started out below the x-axis, and it ended up twice as far below the x-axis as it was originally. There's the vertical stretch. Let's look at the vertical compression, vertical shrinking by a factor of 1/2. What we want is y equals 1/2 times x plus 2 times x minus 3 times x minus 5. And I guess I could have done that with a different color ink. Maybe I'll just erase that one. The original is still this. Let's go maybe a darker blue. This is the original. And basically we want to push points closer to the x-axis than they were originally, so that they're half as far from the x-axis. And I'm going to try to use the economy of keystrokes here. In front of the 2, I would like to insert 1 divided by, basically changing that, or effectively changing the 2 to a 1/2. To do that, while the cursor is flashing on the 2, press second and then the delete button, which will actually be the activate the insert function, second insert, and then press 1 divided by, press the right arrow to stop inserting new characters, and so it's 1/2 times all of that. When you press graph, since we changed one of the equations, it'll regraph all of them, both of them. So here is the original this time, and then the result after the vertical shrinking. It shoves the graph down closer to the x-axis than it was. So the y-intercept, which was 30, is now 15. This point 4, -6 is now 4, -3. The x-intercepts, again, did not move. -2, 0, 3, 0, 5, 0. So we've got the visual. That's the connection between multiplying by a number greater than 1, multiplying by a number between 0 and 1. Let's look then at the horizontal stretches and shrinkings. Here we're doing a substitution. We're substituting either 2x for x or 1/2 x for x if we want to shrink horizontally by a factor of 1/2 or stretch horizontally by a factor of 2. See what the calculator does with this. Same viewing window as before. I'm just going to keep tweaking the second function to make it do what we want it to do. Actually, the substitution, we really should think of it as a substitution not multiplying by 2, because we get here y equals 2x plus 2 times 2x minus 3 times 2x minus 5. That 2x has to show up in all 3 places in order to make the horizontal shrinking happen. So we're going to shrink horizontally by a factor of 1/2. On the calculator, I'm going to delete the 1/2 out in front. And in front of each of the 3 x's, substitute the number 2. So move the cursor so it's flashing on that first x. Press second, insert, and then type a 2. Press the right arrow about 5 times to move to the next x. And then press second, insert again. Press another 2. And then the last one, second, insert. Insert a 2 in front of that. It will redraw both of them, the original. When you press graph, redraws the original and then the horizontal shrinking. There we go. So points get shoved closer to the y-axis than they were originally. Each x can get by with being half as big as it was originally because we're going to multiply by 2 before we evaluate the function. The y-intercept doesn't move. 0, 30 stays right there because we're taking the x coordinate and multiplying by 1/2. So half of 0 is 0. The x coordinates, this one goes from -2 to -1. This one goes from 3 to 1.5. This one goes from 5 to 2.5. All the x coordinates of points on the graph get cut in half. Last one of these 4. We're going to stretch the graph horizontally by a factor of 2. So that would be the f of the 1/2 x. That's going to be y equals 1/2 x plus 2 times 1/2 x minus 3 times 1/2 x minus 5. 1/2 x gets substituted for x wherever we see an x. So, the graph, again, economy of keystrokes rather than typing the whole thing. I'm going to have the cursor on the 2 and I'm going to insert a 1 divided by in front of that 2 to change the 2 to a 1/2. Second, insert 1 divided by. Again, second, insert 1 divided by. And then the last one, second, insert 1 divided by. And we can graph the original, and then it should stretch the graph horizontally by a factor of 2. And it does. Points move twice as far from the y-axis as they were originally. -2. I'm going to rest my hand on the screen. It hits that show desktop or don't show desktop button. -2 to -4. 3 to 6. 3 to 6. There's 6. And 5 all the way over to 10. The y-intercept does not move. Points on the y-axis do not get moved by horizontal stretches and shrinkings. The last 2 of the transformations, I promised 10 transformations in this section. I do not want to disappoint you there. So the last 2 are going to be reflections. They do not involve the number 7. Y equals f of x. I want to reflect the graph, or I want to be able to reflect the graph about the x-axis by tweaking the expression on the right-hand side. So I want to reflect the graph about the x-axis. So imagine the x-axis, points above the x-axis have to move below the x-axis, and vice versa. If a point starts out below the x-axis, it has to move to the corresponding point, same distance from, but on the other side of the x-axis. What coordinates are going to have their signs changed if we jump back and forth across the x-axis? The y coordinates. Positive y's, negative y's. Negative y's, positive y's. So to make that happen, it's got to be outside the f of x so it can affect the y's. So how about this? Y equals f of x changes to y equals the opposite of that. Negative f of x. That's going to change the sign of every y coordinate, and that's going to result in an x-axis reflection. Let's go ahead and do one of those. With this one, if you're not tired of it yet, or even if you are, let's try multiplying by -1 to make this happen. I'm going to delete all the 1/2s first. Just pressing the delete instead of the insert. So delete all those 1/2s. And then back to the beginning. Just want to insert a negative sign. Negative sign right at the beginning of that second expression. Second, insert negative sign, not a minus. Minus will result in an unhappy syntax error. I'll put the negative sign there in front, and this should give us an x-axis reflection. So there's the original, yet again. And then after the x-axis reflection, you see the x-axis symmetry. If we take the union of the two graphs, got x-axis symmetry, and so we can see the two different functions being graphed here. Last transformation. We want it to reflect the graph about the y-axis. That's what we want to happen. And if it's going to affect points, move them from the left to the right, or from the right to the left of the y-axis, what coordinate is going to get its sign changed in that case? X's are positive over here, but negative over there, negative over here, positive over here. So we change the sign of every x coordinate. To make that happen, the negative that we're going to put in here has to be closely associated with the x. So what we're going to do is substitute negative x for x wherever we see an x. When we do that, that will reflect the graph about the y-axis. So back to this picture. Whoa. I'm seeing the same thing you are. Try that again. Okay. What will it show us the next time I do this? Maybe a part of the graph, but nothing else? Oh, the whole thing. Okay, good. Y equals, delete the negative sign from in front, but insert a negative sign in front of each of the three x's. Insert a negative sign there. And insert a negative sign there. And insert a negative sign there. Substitute negative x for x wherever we see an x, changes the signs of all the x coordinates, and it should give us a y-axis reflection. Let's see if it does. There we go. So the union of the two graphs is symmetric with respect to the y-axis. There's one function, there's the other function. If we look at them at the same time, we see the y-axis symmetry after the reflection has been done. Don't care too much for that absolute value example, primarily because some functions, it's kind of hard to tell whether there's been a horizontal or a vertical stretch having taken place. So let's look at this one. We don't know exactly what the expression is that defines this function. It's just a generic y equals f of x, but it's clear what's happened to the right-hand side. Negative x has been substituted for x, and when that happens, what kind of reflection does it result in? Changes the signs of all the x coordinates. Positive x's become negative, negative x's become positive. What do you think? It's a y-axis reflection. Y-axis reflection when negative x is substituted for x. And then, blast from the past, if we add 3 to the right-hand side, it adds 3 to each y coordinate and shifts the graph 3 units which way? 3 up. It's exactly what we would think, hopefully, when the y coordinate is affected. It tends to be the opposite of what we think if it affects the x coordinate. Somewhat counterintuitive. Whoa, putting it all together. We'll put it all together, and then there'll be several more examples after this one. Hopefully it'll stay together. We're given the graph y equals f of x. Now, has anybody finished or attempted the last 2 homework problems in My Math Lab section 2.6? Which ones? Well, 2.6 would have had some difference quotient problems. Would it? I keep saying last 2, but it's problems 9 and 10. I wonder if it's just the last 2 on that page. Maybe I shouldn't say last 2 problems. Maybe I should just say problems 9 and 10 in section 2.6. Those are on the difference quotient, I think, was in 2.5. That's what I'm thinking. Anyway, They're the instructor-created problems where it gives you pieces of two straight lines, basically rays extending this way and that way, and it says f of x equals, and you have to fill in the boxes with linear expressions to define this piecewise function. Well, if you have seen that, what you know is if we wanted to, we could come up with an expression that defines this piece of the graph, and an expression that defines this piece of the graph, and an expression that defines this piece of the graph. If we wanted to. Turns out we don't want to. We've got the graph, and it's reasonably well defined just by this picture, so we're going to go with this picture and see if we can sketch the graph of y equals f of x plus 1, or f of the quantity x plus 1, or a couple others of these, just by looking at the original graph, seeing how it's going to be shifted, or stretched, or shrunk, or reflected. Key points on the graph, of course, -4, 0, and -3, 2, looks like. Maybe down here 1, -2, and 4, 0. We'll consider what happens to each of those 4 points, and then connect the dots, and that will be our transformation. If we add 1 to the right-hand side of the function, it shifts the graph 1 unit which way? Up, up. It adds 1 to each y coordinate. So that's what we want to do. -4, 0 then goes to what point? -4, 1. Add 1 to the y. 0 plus 1 equals 1. -3, 2 goes up 1 to -3, 3. 1, -2 goes up 1 to 1, -1. And 4, 0 goes up 1 to 4, 1. Connect the dots like that, and like this. And that's the graph of y equals f of x plus 1. Just the entire graph rigidly transformed, just shifted, scooted, 1 unit up. Just like that. We have some reference points for that. Suppose, on the other hand, that the action is on the inside of the parentheses, and instead of adding 1 to the function, we're substituting x plus 1 for x. Wherever we see an x, there might be a lot of different x's in the expression defining this function, but we substitute x plus 1 for x. That shifts the graph 1 unit to the left. To the left, so we're going to subtract 1 from each x coordinate. It affects the x coordinates. So -4, 0 goes where? Would you believe? -5, 0. 1 to the left. -3, 2. -4, 2. 1, -2. Goes to 0, -2. And 4, 0 goes to 3, 0. So each point scoots 1 to the left, and it looks like this, and this, and this. So up 1 or 1 to the left, and that's the result. You could think of visually what happens to the graph and shift that up, down, right, or left in your mind, or what happens to each point, just focus on the y coordinates for the vertical shifts or the x coordinates for the horizontal ones. The next couple are reflections. So what I want to do is paste these right here, but we really need the original graph as a frame of reference. So I'll go with this edited version of y equals f of x. Put it right, oops, sorry. Put it right there. This is what we started with, y equals f of x. If we multiply the right-hand side by -1, y equals -f of x, that is what type of reflection? Y equals -f of x is going to be an x-axis reflection. So what we need to do to produce that x-axis reflection is to take Points above the x-axis, move them below the x-axis. Points below the x-axis, move them above the x-axis. We can do so by changing the sign of each y-coordinate. What about points on the x-axis? Where do they go? They stay where they are. So negative 4 is 0. When you multiply 0 by negative 1, you get 0. So that stays there. Negative 4, 0 stays there. And I'll go ahead and look at the other. Negative 1, 0 is an x-intercept. It'll stay there. 4, 0 stays put right there. Negative 3, 2 moves down to negative 3, same x-coordinate. Negative 2, opposite y-coordinate. So it looks like that. 1, 2 goes where? X is still 1. 1, 2. 1, negative 2 goes to 1, 2. Sorry about that. If there had been a 1, 2, it would have gone to 1, negative 2. It'd be great if I could take one of these and superimpose it on the other. That way you could see the symmetry there, maybe. But as it is, this is an x-axis reflection. If we substitute negative x for x, what's that going to do to the graph, the original graph? Y-axis reflection. Now, at some point when I edit my notes, I was hoping to do it this semester. It did not happen. I'm going to change either the negative 4 or the 4 to something else, maybe a 3 or a 5, because something kind of undesirable, at least from my perspective, happens when we do this y-axis reflection. Where's the negative 4, 0 going to go if we reflect that point about the y-axis? Negative 4, 0. On the other side of the y-axis would be where? Well, the y-coordinate is still 0. The x-coordinate changes its sign, and that point goes to 4, 0. How about the point that starts at 4, 0? And we move that to the other side of the y-axis. Where's that going to go? Negative 4, 0. So here's what saddens me about my example that I have created. You take these 2 points, and each one is going all the way to the other side of the y-axis, but the way it ends up looking is like nothing happened. We still have those same 2 points. What's hidden from view is that they've actually swapped places. I guess I could color them. Maybe the original ones, color this one blue, this one red, and that's where that point went. And the other one's blue, and that's where it went, something like that, so you can see what went where. But we have these same 2 points. Now, in the middle, there's actually some changes that take place. Negative 3, 2 keeps its y-coordinate of 2, but the x-coordinate changes its sign. So it becomes positive 3, 2, right there. 1, negative 2 keeps its y-coordinate of negative 2, but its x-coordinate changes its sign. So it goes to negative 1, negative 2, just like that. So we connect the dots like this, and this, and this. Does it look like it got flipped about the y-axis? Here's to hoping that it does. Now there's one more of these. If you did find the notes, I eventually posted them right before my 8 o'clock class yesterday. There's a y equals f of negative 4x that we should also look at. It's just that you can't get to the graph of y equals negative 4x in one step, in any of these 10 transformations, from the graph of y equals f of x. It takes 2 steps. Good news, though, is that we've just done one of those 2 steps. So I'm going to put this one all the way over here. That's where our final answer needs to be. I'm going to take this one we just got through doing, where we refed y equals f of negative x. That was the y-axis reflection. and then consider the original one, and I guess I need the points on the original one. So I'll look at the modified version right here. Up a little more. This is the original that we would have started with, and put that here. So it's two steps. First, we reflect it about the y-axis, and that gives us the graph of y equals f of negative x. And then from there, we need the graph of y equals f of negative 4x. Now that involves a substitution. Basically, we have this, and we pick up the x, and in place of that x, we put what? If we want to end up with this. What do we put inside the parentheses? What goes inside there? 4x. Yeah. 4x goes inside there, just like that. And then we simplify. There's not much simplifying to do. By simplifying, I mean erase that inside set of parentheses. And then we have minus 4x. But if we think about it as a substitution, when we substituted 7x for x way back here, what was that supposed to do? It was supposed to shrink the graph horizontally by a factor of 1/7. X could get by with being 1/7 is great because we're going to multiply by 7. Well, if we substitute 4x for x in this middle graph here, we're going to take this middle graph and shrink it horizontally by a factor of the reciprocal of 4. It's going to be 1/4. And the negative sign is kind of in the way here. The thing is what we're to do, because the negative sign was part of this that we're kind of starting with, this intermediate step. The negative sign really is already been done. So it's only the 4x. So when x gets replaced by 4x, then all the x's get multiplied by 1/4. That's what's going on here. So we got to shrink it horizontally by a factor of 1/4, which means we multiply all the x coordinates by 1/4. So what is 1/4 of negative 4? Negative 1. Y coordinate stays right there. So that point goes to negative 1, 0. Negative 4, 0. We're shrinking here horizontally. So negative 1, 0. 4, 0. What's 1/4 of 4? Take that 4, multiply by 1/4, and we get 1. So there's that. The entire graph has to fit in between those 2 points. Just compressed, shrunk, horizontally by a factor of 1/4. So, how to do it? 3, 2, we take 1/4 of 3 and we get 3/4. So the point 3/4, 2 is right there. We take 1/4 of that x coordinate, negative 1, and we get negative 1/4. So negative 1/4, negative 2. The y-intercept, 0, negative 1, stays put. So 0, negative 1, and the graph looks like this as a result of the horizontal shrinking by a factor of 1/4. Now suppose we're trying to sketch the graph of y equals f of negative 4x. And we're not thinking about transformations. We're just thinking, I've got an x coordinate of 3/4, and I wonder, what should the y coordinate of that point be? I don't know why 3/4 is so important to me, but it's one that I can actually answer. So what should the y coordinate of that point be? Well, I would substitute 3/4 for x. So it would look like this. Y equals f of negative 4 times 3/4. So that's f of, what is negative 4 times 3/4? Negative 12/4? Or maybe, what's negative 12 divided by 4? Negative 3? maybe. Like that. How would we figure out what f of negative 3 is? If this is the graph of y equals f of x. If we have the graph of the function and we want to know what's f of negative 3, how would we determine such a thing? There's probably a point on this graph that could convey this important information. If only there were a point on the graph that had an x-coordinate of negative 3. I'm thinking there is. And there's only one because the graph passes the vertical line test. I'm going to say that's 2. So that tells us what the y-coordinate of that point ought to be. It ought to be 2 because that's what we get when we evaluate the right-hand side. Or we could just shrink the graph horizontally by a factor of 1/4, and that does the same thing. All right. This, I think, is intended to resemble a MyMathLab problem, specific MyMathLab problem. So let's look at this and see if we can find the correct sequence of transformations that will get us from the original graph to the one that's indicated here. So the original one is y equals the absolute value of x. I'm going to highlight that. We've done a little bit with that graph, but maybe not as much as could have been done. So this is what the graph of y equals the absolute value of x looks like. And we're going to transform it into, let's see, the final answer I'll put in dark green. Dark green. We want the graph to look like this. And we'll figure out maybe what an equation of that should be in a moment. If we're going to get from the blue graph to the green graph by doing transformations chosen from among the 10 that we've looked at, start off with the reflection it looks like. You think it would make sense at some point to reflect about the y-axis or to reflect about the x-axis? To get where we're going to go, reflect about the x-axis, think maybe. What would happen if we start with the graph of the absolute value function, the blue graph, and reflect it about the y-axis? What would happen to that blue graph after a y-axis reflection, given that it kind of has y-axis symmetry? It was, well, if we do the y-axis, I mean, we want to do the x-axis. That's the correct answer, right? X-axis. So we're gonna rule out this, and we're gonna rule out this. That's what's not to do. So I'm just suggesting, why not? Why wouldn't we want to reflect about the y-axis? Why would that do us no good at all? You take a graph that's symmetric with respect to the y-axis, and you reflect it about the y-axis, and what happens? It's still the same. Nothing happens, right? Points on the right go to their corresponding points on the left. Points on the left go to corresponding points on the right. They swap places, but the picture looks the same. No change. So we don't want to reflect about the y-axis. Well, we could. Just don't tell anybody. No one will ever know. But what helps is reflecting about the x-axis. When we reflect about the x-axis, it does this. Get this red graph here. That's what the picture looks like when we reflect about the x-axis. So what does the equation look like when we reflect about the x-axis? Take the right-hand side and do what for an x-axis reflection? That one. What do you do the right-hand side? Multiply by -1. And we get the graph reflected about the x-axis. So over there, y equals the opposite of the absolute value. And then we still need to get from the red graph now to the green graph. So we've got to go sideways and up, it looks like. Well, let's go sideways first. 3 to the right or 3 to the left to get toward the green graph. Which one's going to take us up underneath the green graph? Take the red graph, shifting it 3 to the right, or 3 to the left. This is where we want to be. I know you're thinking it. This basically, since they both of those go 2 units up, it's got to be this way, huh? 3 to the left, and then 2 up after that. We're going 3 to the left. What would that look like as far as the equation is concerned? How do we go 3 units to the left? What goes in there inside the parentheses or the absolute value bars? X plus 3. X plus 3. X plus 3 it is. That will shift the graph 3 units to the left. And then finally, we've got to go 2 units up to get to the green graph. So from y equals negative, absolute value of x plus 3, to the green graph, what should we do to the right-hand side to go up to? When it affects the y-coordinate, it's exactly what we would think it would be, is plus 2. So going up, we add the positive number. Down, we subtract a positive number. Or we could just circle B, and we accomplish the same thing. I think the MyMathLab problem is multiple choice. Hopefully it is. I'm going to skip that one. And I'm going to skip most of those. Let's look at example 14. Just the A, B, and C part. So again, the absolute value function. We don't see the picture. We could draw the picture if we wanted to, but we don't want to. We start with y equals the absolute value of x, and we want to shift the graph 3 to the right and 2 units up. What should the resulting equation look like? Three to the right. Substitute what expression for x? To go 3 to the right. X minus 3. After we do that, 2 units up. We just did that 2 units up. What is that? Plus 2. Okay. So y equals the absolute value of x, the quantity x minus 3, and then plus 2. That will shift the graph 3 to the right and 2 up. Try the squaring function. It's a parabola. It's basically, well, I skipped it. Well, I don't know the picture of it. It's a parabola with its lowest point at the origin, vertex at the origin. 2 units to the left. Think of it as a substitution. We're going to pick up the x, replace it with an empty set of parentheses, and inside those parentheses, put what? To go 2 to the left. X plus 2. Counterintuitive, but x here can get by with being 2 units less. Putting the graph to the left, because we're going to add 2 before we square. Then reflect it about or in or through or with respect to the x-axis. How do we accomplish that x-axis reflection? Y equals this. We want y to be the opposite of that, so we jump to the other side of the x-axis. So it would be the opposite of that if we multiply by -1. That does it. And then C. A lot of things, 4 things I think, at least, that we have to do with x cubed. Y equals x cubed. First, 4 units to the left. 4 to the left. So think of it as a substitution. Pick up the x, replace with an empty set of parentheses. Inside those parentheses, how do we go 4 to the left? X plus 4. And then, okay, stretch vertically by a factor of 3. What to do to the right-hand side to stretch vertically by a factor of 3? Where was the stretch vertically by a factor of 7? This one. So this somehow. multiply the right-hand side by what? Vertical stretch affects the y, so it's exactly what we would think. If we want to stretch vertically by a factor of 3, we multiply the right-hand side by 3. And the y coordinates will be 3 units, or 3 times. 3 times as great as they were originally. Y-axis reflection. How do we do a y-axis reflection? Change the signs of all the x coordinates. So substitute. I'll even put parentheses in there, although you can probably do without the parentheses. Substitute negative x for x wherever you see an x. Well, I just see an x one place, so I will substitute negative x in that one place. Maybe lose the parentheses after you put the negative x in there because you really don't need them in this case. Finally, 2 up. Been there, done that. Y equals 3 times, I'll lose the parentheses now, negative x plus 4 quantity cubed plus 2. Yes, it would have been fun to have examined the graph throughout this process and watched it change. But there's only so much fun we can squeeze into a 75-minute college algebra class. Oh, what else? I think I'll skip that one since it's been done for us. And that one, little multiple choice. Multiple choice helped to solidify some of these ideas. Nice one here, perhaps. So we got y equals something. Don't know what the something is. Just represent it with f of x. If we substitute x plus 5 for x, then we're going to shift the graph 5 units, up, down, right, or left. Left. Yes. What if then we multiply the right-hand side by that negative 1 right there, or the negative sign? X-axis or y-axis reflection. On the outside of the f of x, it affects the y coordinate. If it affects the y coordinate, it's jumping back and forth about the x-axis. And then, gotta think of it as a substitution. Not multiplying by 3, but substituting 3x for x in that one spot where we see an x. Back when we substituted 7x for x, what was that? It was the opposite of what we might have thought it would be. We shrunk horizontally by a factor of 1/7. So if we substitute 3x for x, we're going to shrink the graph horizontally by a factor of 1/3. Shrinks it, compresses it like that. Probably B part. There's a B part. What if we substitute 1/5 for x? 1/5 x for x. X has to be 5 times as great as it was originally, because we're going to multiply by 1/5 before we evaluate the function. So somehow it multiplies all the x coordinates by 5 and does what to the graph? Stretches it horizontally by a factor of 5, just like that. Then there's an extra step thrown in here. May or may not be helpful, but we're substituting negative x for x. And we get this. It's going to change the sign of every x coordinate. Positive x's become negative, negative x's become positive. So what kind of reflection? Jumping back and forth about the one that does this, the y-axis. There we go, straight up and down. And then -6, finally an easy one. Subtract 6 on the outside, 6 down. Oh gosh. One of these is tricky, I think it's this one. Yes, the final one in this list is on the tricky side. But it's better to see tricky ones in the notes than tricky ones on the test. Maybe they'll show up in both places, who knows? But definitely in the notes. Y equals f of x. We're going to transform this by substituting 4x for x. X's can get by with being only a fourth as great as they were. So what does this do? It shrinks it horizontally by a factor of 1/4. Multiply the right-hand side by -1, multiplies all the y coordinates by -1. Positive y's become negative, negative y's become positive. What type of reflection? Jumping back and forth about the x-axis. And here's the one. No peeking here. Without this little simplification, and without all these ones here, I think it would be really tempting to say this shifts the graph 4 units to the left. Would you be tempted to say it shifts the graph 4 units to the left? It kind of looks like we're adding 4 on the inside. And when we've sort of done that in the past, half hour or so, it shifted the graph 4 units to the left. But we got to think of it not as adding 4 on the inside by substituting x plus a number or x minus a number for x, and then simplifying if necessary. So here's the thing. We've got y equals negative f of 4x. If we pick up the x and replace it by a soon-to-be not-so-empty set of parentheses, the question is, what expression should go inside those parentheses so that when we distribute the 4 across and clear it, we get 4x plus 4. What goes inside the parentheses? X plus 1. So actually we're substituting x plus 1 for x, and when that happens, that shifts the graph to the left for sure, but only 1 unit to the left. So we don't need that, we do need that. But yeah, without this, and without all the ones, maybe give you some 4s to choose from as well, I think it would be tempting to say this shifts the graph 4 units to the left. All right. Anything else that needs to be talked about? There's some other examples. They might be skippable. I mean, by this time, there are only 10 transformations, and I think there they are right there. Up, down, right, left, vertical stretch, vertical compression, horizontal stretch, x-axis reflection, y-axis reflection. But we've talked about them all ad nauseum. So that's a good place to stop.